Okay, we're in chapter 5, and so now already, what happened to? Oh, that we started. 4 was the last one. Okay, and so we have Euler circuits, so that must be resistors and capacitors and things, right? And then we have graphs, and then we have graph concepts and graph models. Um, I guess we don't use resistors and capacitors. I don't suppose so. Um, we're going to start in the 1700s in some town in Germany, and this guy by the name of Euler decided that he wanted to walk to each of the islands of the town, and he's got 1, 2, 3, 4, 5, 6, 7 bridges, and he only wants to cross each bridge once, and he wants to know whether or not he can do that, and without using a bridge more than once. So you have an Euler path, and a path would be, I'd start over here, I'd go over there, that'd be a path. I could go here, I could come back, I could come over here, that'd be a path. Or I have a circuit, I have to go across each bridge only once. And if you look at that real quick, you'll see I can't do that. Because if I go this way, and I go that way, then I'm this way, and then I'm that way, and then I'm this way, then I'm hosed. If I go that way, I'm stuck there. If I go that way, I'm stuck there, and I can't do it. So there must be some reasons, and this is supposed to be a walking around problem. We'll get to much better things later on in the chapter. We'll see whether or not the mailman can deliver the mail. And this is the beginning of graph theory. I took a graph theory class as a graduate class at UNO, but the computer science guys were in the same class, and it was undergraduate for them. So, but this is good for garbage collection, mail delivery, police patrols. When I was a Coca-Cola repairman, we did the same thing. We would leave the Coke plant, go this way, do a circle around town, come back to the Coke plant. We wouldn't go here and there and here and there and here and there and here and there. We wouldn't do that. That'd be silly. And routing problems. I'm trying to get to Hawaii. It'd be nice to get there for a lot less than what they want me to pay, so I'm probably not going to go to Hawaii. Is the route possible? That's important to know. If it's not possible, then why do it? And is it simple? Yes or no? Is it optimal? So optimal would be another thing that we'd want to know. And Euler circuit problems, lack of a better term, the exhaustion requirement. It's a requirement that you find the best route, and you have to go everywhere. So that's not good. Then, of course, there's private security trying to prevent people stealing things in the neighborhood. So here we go. We're going to walk around the hood. This is irrelevant because at the end of his patrol he needs to be back at S. So can he leave S and go past everything and still get back to where he was without going the same way twice? And it looks sort of like he can't, but I'm sure it'll tell us anyway. Being a practical person, the security guard would like the answer to 2 questions. Is it possible to start at S, cover every block of the neighborhood, and pass through each block only once? If some of the blocks will have to be covered more than once, what is the optimal route that covers the entire neighborhood? Optimal here means the minimum of time he has to walk. And the mail delivery man, he has the same thing, but he has houses with boxes on both sides of the street. So he's got to go down both sides of the street when he walks. So that'd be a different thing. So the postmaster has to walk down both sides of each of these streets in order to get everybody. And so that would be a different type of problem. The mail carrier has no choice. He has to start and end at the post office, but he wants to find an optimum route that would allow him to cover the entire neighborhood because he's going to do it 300 days a year. He wants to make sure that he doesn't wear out his shoes. So now we're going to go back to the 7 Brigses of Coinsburg. Is that Coinsburg? Must be. And we have a regular type map. We have a map that looks like that. And we also have the bridges of Madison County. Can we go across them? So here we are, bridges of Madison County. So there, over here, across there, down like that, this way, that way, up, this way, up that. I didn't make it. I didn't go across all of them.
However, though, one of them is burnt down now.
Which one?
I don't know. I just know one of them burnt down.
Oh, one of them burned down? Oh, well, that might have changed the problem. I might be able to do it.
Just saying.
Yeah. I think the issue is going to be these two guys have odd numbers of bridges. So how am I going to get across one and across another? And then through the other one without, and then I can't get out. So if I start at D, I could end at D. If I started at B, I could end at B. But if I started any place else, and I went to either of those, I wouldn't be able to make it. Few simple drawing lines, and all right. So here we go. Now we're gonna go and do it with just traceable lines. So forget about the bridges. Forget about Madison County or Coinsburg. We're going to go, and so this connect the dots. So if I start here, 1, 2, 3, 4, 5, 6, 7, 8, 9. I blew it. I didn't make it. All right, how about here? 1, 2, 3, 4, 5. Nope, didn't make it there either. Oh well. I'm certainly hoping that in the next section we actually find some rules to do. This guy here looks pretty complicated. Hope we never have to do that. Oh, done with section 1. Wow. I wonder if there's any section 1 problems. Probably not. Yeah. Typical. Yeah, section 1 problem. So we're looking exercises. Section 1. No, nothing there we can do after doing section 1. Wouldn't you know it? Okay. So that was section 1 was vocabulary. See whether or not I could pronounce German words. All right, section 2. What is a graph? It's dots, which are vertices, and it's lines, which are edges. So a graph has dots, and because we're adults, we're going to call them vertices because we have to use multi-syllable words. And then we have lines, which we'd call edges, and they both have the same number of syllables. Right. On the surface, that's all there are. The lines connect the dots. But there's a rich theory involved. I can imagine how rich it is. Gold, maybe. So some basic concept. We have 6 vertexes, A, B, C, D, E, F, G. Now here's F over here. Huh?
There's no G, just F.
Oh, F, okay. So F isn't connected to anything. He's not much of a vertices, but that's okay. We have vertices. Each edge can be described in any order of pairs. So I have A to B, or I could have B to A. They'd be the same edge. I have A to D, I have D to C. I have 2 D to C's. I have a B to B. Okay, so I got edges, so there's edge B to B. I'm sure the next slide is going to say something like the vertices at A here has some degree, and that degree is 2 because there's 2 edges going into it or something like that. Okay, note it. What happened? I just slipped a very important slide. I doubt it. All right. Sometimes edges will cross each other, and sometimes they don't. So here they're crossing. But I wouldn't necessarily have to have them cross. I could have A way over here, and I could have D be a circular path over there, and this guy coming back. So, you know, it's just I drew them crossing, but there's no vertex. In such cases, they're creating there's an AD and BE, but there's no vertex where they cross. All right. Edges have do not have a direction. So there's no right or wrong way to call it A to B or B to A. It doesn't matter. It's just an edge. Think of A as being a computer on the Ethernet and B being a computer on the Ethernet, and they're talking to each other. No, don't think about it that way. Much too complicated. All right. So we have vertexes A, B, C, D, E, F, and we have edge sets, a set of edges. And I'm sure we'll have to go to write down what they are. Notice that CD appears twice. CD appears twice. That's because there's two of them. Oh, isn't that nice? We could call that a multiplicity of two, probably. Imagine that I have a sociology study. We want to describe the network of friendships that develop among a group of students through their no, we don't want to talk about Facebook. We can illustrate it very nicely by having vertexes being the student X and Y, and the friends going the other way. So here's my vertexes being the friends, and now we have an inner relationship between those friends. So it looks like Betty likes everybody except Veronica. And Veronica can't stand anybody but Archie. Okay, so now we could do that. We could have no edges. So we'd write no edges with brackets with no edges, or we could use the null set, the phi, Greek letter phi for the null set. These are isolated vertices, they have no edges. See how rich the theory is? I have nothing. I was reading something about the physics people are having a difficulty describing what nothing is. You know. Well, if you have nothing, do the laws of physics still apply to the nothing that you have? Yeah, well then you have something because you have the laws of physics. What a bunch of whatever. Okay, well, here we go. So here we have a picture. We have vertices A, D, L, R, and we have edges between those vertices. But where's the picture? All right, so there we go. So I could do it like this, nice and orderly picture, or I could do something with squiggly lines using my crayons, and they're equally the same. They're the same graph. Perfectly okay to do it either way. Right? So there's nothing more right about the guy on the left or the guy on the right. Clearly the guy on the left is more aesthetically pleasing. And we could make that thing. You know. Pictures are optional. So we're going to do the same thing, same set of sets. One looks bad, one looks nice, but they're equally okay. Important point. We think of a graph as a picture consisting of dots and lines, but the picture is just a visual representation of some more abstract idea. A set of vertices, a set of points, and we have a graph. So a graph is a structure consisting of a set of objects, vertices, and a list of describing how those pairs of objects are related to each other. Relationships among the objects include the possibility of being related to oneself. So I could be my own father, for example. That's possible, right?
No.
I can't be my own father?
Well, I guess you could if you married your mother.
Yeah, I could marry my mother and be my own father. Right? I could. As well as multiple other things. Okay. Well, I could go back in time. Marry my mother and be my own father. Yeah, I could do that. Yeah. I can't think of any good reason to do that. Okay, now we'll come back to the homework and see whether or not we can do homework problem number 1 yet. Okay, for the graph shown below, find the set of vertices. Okay, so we need a thing there. So number 1, A. the set of vertices.
A, B, C, X, Y, Z.
Oh, perfect. A, B, C, X, Y, Z.
Oh.
Is that good?
I don't think it would be.
There's no B? There's a B.
Yeah, no.
He said he doesn't know if he can
You
handle
don't,
B.
can't handle these?
Yeah.
Oh, yeah, these are. Now this is going to be difficult because you can't just put something like that. It's got to be a written E type thing, so it has to look funny like that. That's not funny enough. Let's see. Yeah, that's better. So now I'm going to list my edges. AX, AY, AZ,
X, Y,
XY,
XB,
XB, XC,
BC,
BC,
and BB.
BB. Very good. All right, now you don't know anything at all, but you can still do problem number one. What more can we? Now we have to list the degree of each vertex. Okay, so the degree of vertex A. How many? I think it's spelled D-E-G probably. Yeah, that's probably better. Degree of vertex A. 1, 2, 3. Yeah, because there's 3 edges. The degree of vertex B. 1, 2, 3, 4. Degree of vertex C. 2. Degree vertex X. 1, 2, 3, 4. Degree vertex Y. 2. Degree vertex Z. 1. All right, so we did problem number 1. We're now looking at problem number 13, and consider, can't do 13 yet. Okay. So we made it through section 1 and section 2 already, and you guys are going to make me stop at section 4. That'd be okay, We'd still take the same quiz. Whether or not we could do any of it, that'd be a different issue. Concepts. Okay, concepts. I thought we already discussed terminology. We have vertexes, we have edges, we have degree. What more can we want? And what kind of concepts can there be? Every branch of mathematics has its own particular messed up set of words, also known as jargon. And graph theory has more than its share. In this section, we'll try to introduce some of those concepts. Needed in the next 3 chapters. Oh, good. We don't do chapter 7. That's the hard one. Okay. So we're only going to do 2 chapters.
The terminology that we already know, can we just skip it?
We could, yeah. Adjacent.
Just saying, that way we can get more sections.
Yeah. Then we get more sections done.
Yeah.
Yeah. We say that.
What? Haven't you guys ever had this before? I had this back in elementary school.
Well, I'd hope so. Yeah. Well, it's gonna get worse before it gets better.
So that's how that worked out with me.
Okay, we'll just skip to the final and go home. We say that 2 vertices are adjacent if they are joined by an edge. So A is adjacent to B. A is adjacent to C, blah, 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 blah. 2 edges are said to be adjacent if they share a common vertex. So BF is adjacent to EB because they share B as a vertex. On the other hand, AB and DE are not adjacent. Okay, so I can be adjacent as a vertex, or I can be adjacent as a edge. Degree of the vertex. Okay, we went over that already, and I almost spelled it right, except I put V's in there for vertex. So the degree of vertex C, where's C right there? 3. 1, 2, 3. We already said that once. E. We would call that 4. 1, 2, 3, 4. That's so we're counting it right. Now, I can be even or I can be odd on my vertex. Now this is going to be important because if I'm odd I can get away, but I can't get back. If I'm even, I can get there and get away. So I can, and that'll be important to know when we're trying to find a path or trying to find a circuit, how I'm going to get there. 2 even vertices and 6 odd vertices. Probably have a problem, we have to count them. So here we go. A path and circuits both describe trips along the edges of a graph. The only real difference between a path and a circuit is that a circuit is closed. That means wherever I start, I got to stop in the same spot. And the trip ends, let's see, for a closed trip. So a circuit, if I start at A, I got to get back to A. Whereas a path is open, I just start someplace and go someplace, and that's perfectly okay. In this context, by a trip, be it a circuit or a path, we mean the sequence of edges with the property that an edge can only be traveled on once. So when I'm either doing a circuit or a path, I can only be on an edge once. Well, I guess I can't explain why that is because I had no idea, but that's what in 1700 that's what they decided to do. Then I just go one way. All right, so now I've got a path. So I could have a path E to B to F to G. That'd be perfectly okay. But I can't have a circuit anywhere on this thing because, well, I could, because I don't have to travel everywhere. So I have a circuit, I could go E to B to A to D to C. I could do that. That'd be a circuit. I'd travel path once and only one thing. But I don't have a circuit to get to each of those points because if I get out here to G or to H, I can't get away. In fact, anything that's odd, any odd vertex, I couldn't get away from it if I traveled the other parts. Number of edges of the path. The length of the path. All right, so now we have a length. We have a length of the path. We have things that are adjacent. We have vertices that have degree. All right, so A, B, C, D, E is a path of length 5 from A to E. A, B, C, A, D, E. All right, so I can do that. A, B, C, B, E is another path from A to E. This path is also possible because there are 2 edges connecting B to C. So I could have a different path. All right. But those are paths. I didn't get back to where I started. A, C, B, E, D is a path of length 5. A, C, B, E, and then I could go around to E again, and then D back to A. So A, B, C is not a path because A, B is traveled twice. So I cheated and went across A, B twice. I no longer have a path. A, B, C, D, double E, D, A, C, B is not a path because I traveled B, C twice. No, I traveled it 3 times. That's even worse. The first 2 passes are fine, but since because there's 2 of them, but then when I did it a 3rd time, I no longer have a path. B, C, B is a circuit of length 2. B, C, B. I started at B, I went to C, I went back to B. So that's circuit of 2, perfectly okay. E loop is considered a circuit of 1. So I can go start at E, end at E, perfectly okay. Now I have a circuit of 1, a circuit being something where I get back to where I started from. Connectedness and bridges. A graph is connected if you can get from any vertex to any other vertex along a path. Okay, so if I disconnected this edge right here, I am no longer connected. And we call that a bridge. And when I have only one thing going from one edge to another. So now I'm no longer connected and I am disconnected. Oh, isn't that lovely? Connectedness, bridges, and disconnectedness. A disconnected graph is made up of separate connected components. Well, what if I just have this F up here by itself? Yeah, okay, well, we'll allow that. Okay, so there we go, all by himself. Shows a disconnected graph with three components, one of them being an isolated vertex. Okay, so this is the students of the class. This is the friends of the students in the class. And there's the instructor disconnected up there talking to himself because everybody's sleeping. All right, perfectly okay. Figure 11 is the graph we're blah, blah, blah. Remove BF, blah, blah, blah. Okay, well, I just think we just did that, didn't we? This illustrates how removing just one edge from a connected graph can sometimes make the graph disconnected. If that's so, then we call that a bridge. So if I can remove a graph and I'm disconnected, then that's called a graph. Okay. Now we have Euler paths. Okay, an Euler path. So a path just goes someplace. An Euler path is a connected graph. Is a path that travels through all the edges of the graph. Beginning a path, edge can only be traveled once. So an Euler graph does every edge, but it only travels each and only once. Blah, blah, blah. Okay. An Euler circuit is a graph that travels through every edge of a connected graph. Being a circuit, that I have to end up where I started. Okay, so I have an Euler path, I can travel everything, or I can have an Euler circuit and end up where I started from. All right, why not? So now we have this guy, and I'm starting a path at C, and I go that way, and I go 2. That way, this way, this way, that way, that way, that way, that way. Now I started at C, I ended up at D. I had an Euler path. Starting at C. So if I started at D, I could probably have an Euler path. If I started at B or A, could I get an Euler path if I start at B? No, probably not. So it looks like if I have an odd vertex, I can get an Euler path. But if I start at an even vertex, it looks like I may not get an Euler path. Maybe. Oh, now, look at that. Now we got it all hosed up really bad. In the graph shown below, we have an Euler circuit, one of many. If we want to find a different one, we have to do something different. So I'll do the same thing over again. And this looks like something we did when we were kids again, right? Trying to stop our sister. All right, so the graph shown below has neither an Euler path nor an Euler circuit. Now, how is that possible? Is C a vertex or not in this graph?
No.
It probably is. They just left that 0 out. All right, so why doesn't this guy has an Euler path? 1, 2, 3, 4. That wouldn't get there. I didn't go the other way. 1, 2, 3. Yeah, I'm all going to have one side left out. Yeah.
Because they're all odds.
Yeah, they're all odd, and that's the problem, probably. And in section 5.5, we'll figure out why. But right now, it's pretty clear it's that way because there's no even guys there at all, and they're all odds. Oh, look at that. We're done with that section already. Oh, and it's almost time to move on to see if we can solve another problem. Number 13. Consider graph. Okay, we can do that. So we're going to consider figure 5 32. Number 13. Now, who would give number 13 as homework? I mean, that has to be some demented type guy, right? Only some demented guy would do that. C, A, and then we have H sitting over here. G, going to G. F, and E. All right, now, find all the circuits of length 1. Okay. Hey, I'll do that. All the circuits of length 1. G to G. That's the only one. Everybody else has more than that. Okay, so that's A. B. Find all the circuits of length 2. Boom, 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 boom. 1, 2, 1, 2. That's 0. There are none. There's no circuits of length 2. I can't get back to where I started from with only 2. C. Find all the circuits of length 3. Okay, so H, F, G, H. H, F, G, H. Now is H, F, G, H and G, F, H, G, is that the same guy? Yeah, how about F, G, H, F? Is that the same guy? F, G, H, F, and G, F, H, G. And I could go the other way, right? So I could go H, G, F. So I could have H, G, F, H, and F, H, G, F. And I could have G, H, F, G. There's 4 of them. How about these guys? Anybody over here? No one over there. And if I start at E, I'm hosed. I'm not going anywhere. All the circuits of length 4. A, B, C, D. Okay, all the circuits of length 4. So C, D, A, B, C. And all the other guys, right? So I could have 4 combinations of them. 8 combinations because I can go both ways. Okay, so should I put all 8 down? Plus 7 more. How about over here? I could go H, F, G, G, H, right? So I could go H, F, G, G, H. Or I could go F, G, G, H, F. Or I could do that the other way around if I wanted to. So I'd have 2 more like that. What are the total number of circuits of the graph? Total number of circuits. That means I got to figure out what the other ones were here. All right, so I could have a F, H, G, G, F, or I could have a H, G, G, F, H, or I could have a G, G, F, H, G, G, or I could have a G, G, F, H, G, or I could have a, did I leave anything out? No, I think that's probably enough. Okay, it's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So it looks like I have 21 because if I ever cross a bridge, I'm never going to get back, right?
Right.
So I have some over here, I have some over there. All right. 17. 17. Figure 35 shows a mouth downtown, blah, 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 blah. Draw a graph that models this. Okay, so this model of the graph. I'm pretty sure we'll get that into the next section, so, but it's so pathetically easy, we might as well do it now, right? So I'm going to have a North Queensburg as a vertex. Going into B, B going into A going into South Queensburg, going back up into C, C going back over there, and C going into there, and now I've modeled the graph, and I'm done with 17. 21. 6 teams are entered in a softball tournament. The top 2 seeds only have to play 3 games. The other teams have to play 4 games each. The tournament pairing has A against those guys, B against those, blah, 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 blah. Draw a graph that models the tournament. Well, not sure I want to do that yet. I think I want to go and do chapter 4, section 4 first. It may shed some light on it. I doubt it, seriously, but I'm sort of hoping that there'll be a little bit of light. Oh, open. All right, there we go. Section 4. Look at all these words. Can you imagine that?
Too much.
Yeah. Oh, look at that. It's called graph models. Well, you know, one of Euler's most important insights, I can imagine. Converting, paraphrasing, graphing problems, called modeling. Taking a, let's stop for a moment and show for a moment. Come back over to cancel out of there. All right, so this is a very, very interesting mathematical thing. So we have this kingdom of no multiply. Okay, so I have a kingdom where I can't multiply. The king won't let me. All the mathematicians sit around and how are we going to multiply if the king won't let us do it? They say, we will go over to the land of log. And in the land of log, we're going to only add. Okay, so we're going to take our numbers in the no multiply, and we're going to have numbers A and B, and we're going to send them over to the land of log, and we're going to have log A, and we're going to add it to log B, because the king says we can't multiply, right? And then we're going to come back over to the land of no multiply, and we're going to take an anti-log of this answer. We're going to call it C, anti-log of C, and our answer is going to come over here and be that answer, the anti-log of C. Okay? And now we've done what the king said. I'm not multiplying, only adding. Okay? Well, we can do the same thing in graph theory. We can take a problem in the time domain. I throw something up in the air, it comes down or whatever, and I can send it into a graphing domain where I can actually solve the problem, and then once I get the problem solved, I send it back to where it came from. So that's the whole theory of graph theory, that I can think something very difficult that I can't figure out how to do, but I can model it as a graph, now solve the problem and send it back. Okay, so everybody believes that, right? You hit the my believe. Yeah, that's right, exactly. That's why you got a graphing calculator for. So anyway, that's what Euler did. Now, what happens is that then you send all these grad students out to figure out what these problems are that can be done that way. And yes, it can be done, and wasn't it great? And should we really be wasting our time in it? So here we have 7 bridges going through Koningsberg, and there's our map. But it doesn't matter the shape of the islands or the shape of the river. So I could do a graph that it would look like that if I wanted to. That'd be perfectly okay. And then I could just bring it over here. And now all the extra information of where the other roads are or what they're called or anything are all superfluous. I just have vertexes and edges. And now I can use it to figure out if I have any Euler circuits or Euler paths. And I can do the same thing when I'm walking around the hood thing where I have the school or the security or I have the post office. I could go and send it to a bunch of edges, and now it looks like we're playing connecting the dots. And we could do the same thing. We could, does the graph have Euler circuits, Euler paths, neither or both? These are relevant questions but won't be answered today. And then we can deliver the mail, walk around, and now we're doing the same thing with the deliver the mail thing, but now the mailman's got to be on both sides of the street, so I have edges showing both sides of the street, and as my model of what I'm using, and we're done with chapter 4. Excellent, isn't that lovely? All right, so back to problem 17. Is that what we're doing, or did we already do 17? Okay, 21. All right, back to problem number 21. All right, so we've got team A. Plays against C, E, and F. Okay, so team A plays C, E, F. All right. Team B, oh, this is where my multiple colors will be good. Team B plays C, D, and F. Place team C plays F, C.
Every team except F.
Every team except F?
Mm-hmm.
Every team except F.
So the only one
Boom.
D.
And D. Every team except F. D plays against every team except A. D plays against every team except A. And E plays against every team except B. We'll go with this one. Where was I? E, every team except B. Every team except B. Okay, and then F plays against every team except C. F plays against every team except C. He's already doing that. So there, I guess I'm done. I've done number 21. I have drawn a graph that models the tournament.
Putting that E to D, isn't there an extra line in there? You already got it connected.
Well, then we're going to put F.
E.
Yeah, but you can do your
Oh, right here? Yeah, I see that. Okay. Going boom, boom, and put one like that. Is that better?
Yeah.
Okay. Now remember when you do the chapter test to bring in your crayons. No? Oh, you don't have any crayons?
I have
Oh,
markers.
bummer.
I guess if you have markers, please.
Yeah, I'm gonna have to bring in your crayons, otherwise you won't be able to do it. Okay, so that looks good. Now, number 23. Euler theorems, 23. Blah, 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 blah. Okay, page 37. All right. In 23 to 28, only one of the following answers is correct. I, the graph has an Euler circuit. Double I, the graph has an Euler path. Triple I, the graph has neither an Euler circuit nor an Euler path. The circuit has many, may or may not have an Euler circuit. The graph may or may not have an Euler path. Choose a correct answer, A, B, C, and D. Okay, I haven't even figured out what that meant. How am I going to figure out what it... anyway, so we're going to look at the A guy. All right, so I'm looking at the A guy. I'm getting a headache. All right, I'm looking at the A guy. And can I get an Euler path? I don't think I can get no, I don't think I have an Euler path or an Euler circuit. And the reason is I have multiple vertices that only have two guys on them. Yeah. All my vertices are even. And because all my vertices are even, I don't think I can see an Euler path cover all the if I started on the outside, I could get it all the way around the outside, but then once I got to the inside, yeah, I do. Yeah, I do have a circuit. I see a circuit in A, and so, see, what have I got here? I got the graph has an Euler circuit. Yes, it does. The graph has an Euler path. I didn't find it yet. The graph has neither. The graph may or may not have. The graph may or may not have. Okay, so now the issue is, I have an Euler circuit. Do I have an Euler path? No. An Euler path would be, I start at one place, I go through everything, and I end up at a different place. Because I have even number of vertexes as my degree, that would never happen. So for A, it'd be I. I have an Euler path. I have multiple Euler paths because wherever I start, I could probably have multiple ones, but I have at least one. So B, the issue is, I have vertices that are odd. So now, does that give me an Euler path? Well, if I start at any of the
Yeah,
Did you find a path?
If you look, it's just that it has two sides on from the other one, so there'd be no way it could.
Yeah, I'm adding in those guys from the other guy.
So this thing is where.
Yeah.
This exit where there's no circle either, so you can't end up the same place either.
Yeah, I can't do that either.
So
The graph may or may not. The graph has neither. I think this is triple I. It has neither a path or a thing. I think that we're going to find out next week that you need if you have more than one odd vertices, your host. The graph has 6 vertices of degree. A graph has 6 vertices, all of degree 2. All right. So if I have 6 vertices, A, B, C, D, E, F, and they're all of degree 2, it could look like this, right? In which case I could have an Euler circuit, but not a path. But I could have something like this. And that would be a graph with 6 vertices, each of degree 2, and I don't have any Euler circuit or Euler path, right?
You have a circuit. Well,
No, I can't get from here to there, or there to there, and I got to go through all 6 of them. So this would be the graph may or may not have an Euler circuit, may or may not have an Euler path. Okay, we'll go with may or may not have an Euler circuit. All right, so was that fun?
Yes.
That was fun? Keeping the requirements that we not catch up on the syllabus. That means we have to stop unless I find that I can work problem 27. 27. Yeah, I guess we'll stop there. All right, so we'll pass out the quiz. Do the quiz next. Did I bring the quiz? Oh yeah, I got the quiz. Okay.
Do we need to go over the rest of the sections to do the quiz?
Oh, I hope not.
I'll find out.
We'll find out. Let's see. Yeah. Okay, we'll pass out the quiz and do the quiz. It can be overboard.
All right.
Yeah, get as far as we can. Yeah, don't turn the page.
Well, hello.
Anyway, as I was saying,
Oh, that's nice.
clearly we needed to get a little bit further to do the quiz, but that doesn't matter. We'll do the quiz anyway.
We don't have to do it Thursday
Oh,
or Monday.
yeah, we'll have a different quiz Monday. That's all right. We're gonna get 100 on the quiz, right? So I don't. Why should it bother? You know. So as soon as I get ready to do the quiz, we'll. Could be worse. Good thing you didn't try to do the quiz before you came to class or something. too much noise over here. Okay, we done goofing off?
Sure.
Excellent. All right. Anybody know what a Hamilton path is?
No.
Okay, a Hamilton path goes through every vertex, but doesn't necessarily have to go through every edge. So not necessarily. Has a Hamilton path starting at G, ending in. So if I start at G, can I get there? No. I can't. I got to go through every vertex. I can't do it. So I can't do that one. Starting at G, ending at E. No, I can't do that either. But if I start at D, I can go D that way, this way, that way, this way, this way, that way. If I start at D, I can go that way, this way, that way, this way. Yeah, there we go. there, 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 there. So I have a Hamilton path starting there, going here, here, there, there. Now I've gone through every vertex, and but I don't necessarily have to use all the edges. So correct answer is A. And I'm sure on Monday we'll get to that. Repeated nearest neighborhood traveling sales problem is approximate and it's effective. So what you have is you, if I'm here at A and I have a choice, I can go here 10 or I can go there 15. Which path do I take first?
10.
I go to the 10 way, yeah. And then when I get here and I got a 5 and I have a 2, which one do I take?
2.
I take the 2. And I keep doing that until I make it back to A, and that would be my most efficient route, because I'm doing the nearest neighbor thing. Now, if repetitive means I do it again. So if I go this way and I find out that I'm hosed for some reason, then I go that way and try it the other way. A truck must stop off furniture at 4 different locations, starting and ending at A. Okay, so I have to end at A, and I want the most efficient route. So what we're just going to do is we're just going to count the edges. So if I go A to B, that's a 9. B to D, that's an 8. D to C, that's a 1. C to A is a 4. 22. So that's my A path. My B path has me go A to D for 5, D to B for 8, B to C for 2, and C to A for 4. Okay, and that's 19. And then I do it again. So my C answer says I start at A, I go to C for 4, and then D for 1, and then B for 8, and then A for 9, 10, 22 again. And then my D answer, A to B for 9, B to C for 2, back to D for 1, up to A for 5, for 17. So D wins. So, and that's what we would do. We'd go every single route to see which is the minimum route. Now, clearly if we have 10,000 vertexes, we better come up with a better way, right? But with just a few vertexes, that's what we do. And normally in a problem like that, you could guess D and go and move on, because it's going to be, they're forcing you to do the wrong ones before you get the right ones. So I would probably work it in reverse order. D for, no, you got to do them all anyway, right? So it doesn't matter. Yeah, you got to do them all anyway, it won't matter. Okay, here we go. Isn't this lovely? Nearest neighbor starting at C. Okay. The graph below shows the distances between locations. We want to minimize the total distance traveled. All right. So we start at C. We start, where the hell C? Here's C. Okay, we could go to B. We could go to A. We could go to F. We could go to, so the nearest neighbor is A. C to A. Okay, once I get at A, I have a 2.420. I have a 19. So going to B would be the shortest route. CAB. So I don't have to go. Well, still could be none of these. Darn. All right. So now I'm at B. 1.1 is delta. Okay, I'm at delta. 1.4 is F. I'm at F. 1.3 is E. I'm at E. and I go back to C, and that is, and we said, what did we say? We said it was B, and right there we said it was B. Or did we set it back here someplace? Wherever we said it was B, and it turned out to be B, but it could have been none of the above, so we'd have to do the whole thing anyway. But so we're going to call it B. But that's what, and that would be the nearest neighbor thing. Now, this is a K-graph that has an edge going to every other person. So I can always get around, always have a path to get there. All right. Last problem. Hamilton circuit has K11. So that means I have 11 vertexes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 vertexes. And I have an edge going to every vertex. And we want to know how many different circuits there are. So if I have 11 vertices, and from each of them I have 11, I have one going to each one like that. How many edges do I got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 10 of them. All right. So I've got 10 factorial circuits on that guy. Because once I leave this guy and go someplace else, I have 9 left to travel. Once I leave that place and go someplace else, I have 8 ways to go. Once I leave him, I got 7 ways to go. Once I leave him, I got 6, and that's why it's 10 factorial. Okay, put your name and your test grade on your quiz, and then I'll hang out here and enter it in the grade book, and I'll see you on Monday. And we'll finish on Monday. We'll finish chapter 5 and 6. No, just kidding. Good idea. Excellent idea. Good thought. And we're almost done with 5 anyway after doing this quiz. We covered everything we didn't cover yet. All right. But it'll clearly take me at least an hour to get the PowerPoints on the website. Another such nonsense. Oh, and midterm grades aren't done until Wednesdays. I don't have to do that until Monday quiz is over. Yeah, that'd be good. All right, bye-bye.